In this video, we're going to talk about the two primary modes of energy transfer that we're going to deal with in this course, and those are heat and work. Heat, which is typically represented by a lowercase q, is the energy transferred by the random motions of particles. Work, which is represented by a lowercase w, is the energy transferred when an object is moved against a force, right? So, especially with work, you have to be careful because something has to be moving and that movement has to be against a force. So, for example, if something is traveling through a vacuum by just simple inertia, that would not be considered work because there is no opposing force acting on the object. Okay, so we're going to go back to our system surrounding diagram, and we're going to look at how to use these diagrams to interpret qualitatively what's going on with heat and work. If the system is doing work on the surroundings, then we say that the work is less than zero. Another way of saying that is to say that the work is negative. And what it means for the system to do work on the surroundings, it could mean a few things, but the type of work we're going to deal with is expansion work, which means that the system is expanding or increasing in volume and pushing against the surroundings. So we're moving basically the boundaries of the system against the force of the surroundings, and that would be negative work. The opposite would be if the surroundings pushes against the system. Then our work would be greater than zero, which would make it positive. So in other words, if the system is contracting, if it's getting smaller in volume, that means the surroundings is pushing against the system and doing work on the system. Therefore, work from the system to the surroundings is negative, work from the surroundings to the system is positive. Another way of saying that is work on the surroundings is negative, work on the system is positive. Heat works the same way. If heat leaves the system, so if the system cools down and the surroundings heat up, then we say that Q is less than zero, or the heat is negative. If heat enters the system and the surroundings cool down and the system heats up, then Q is greater than zero and the heat is positive. Therefore, system cooling is negative heat, system heating is positive heat. Okay, so let's look at a specific example. We're going to go back to our balloon that we had in the previous video, and now we're going to look at this from the perspective of work and heat. If we have a gas-filled balloon held over a flame, we can see that the heat from the flame is going to go into the balloon. So heat is coming from the flame and going into the balloon. And remember, we said last time that we're going to consider the balloon as our system. So if heat's going from the flame into the flame is part of the surroundings, the balloon is our system. So heat is going into the system, which means Q is greater than zero, which means it's positive. Okay, so heat came from the flame into the balloon. Now this is a balloon filled with gas, and we know that when you heat a gas, by the ideal gas law, that gas expands. So therefore the volume of the balloon is going to increase because the heat is going into the balloon, which accelerates the particles inside the gas particles inside the balloon. Therefore they hit against the walls of the container, in this case the balloon, with a greater force and a greater frequency. Therefore the balloon borders, or the edge of our system, is going to push against the surroundings. In this case, the surroundings it's pushing against is the surrounding air. Remember, all of the space around the candle and the balloon is not empty, it's filled with air particles. The balloon is pushing those air particles out of the way as it expands, therefore it is working against the opposing force of those air particles, the pressure in the air. So work is being done on the surroundings by the system, therefore work is less than zero, and it is negative. Now, I'm going to put this into our system surrounding diagram because on an exam or on your homework or something like that, it's much faster to draw something like this than it is to try to draw an accurate sketch like this. So if you can just draw these concentric circles, label which one is the system, which one's the surroundings, you can quickly show that heat is entering the system from the surroundings, therefore Q is positive, and the surroundings is doing work, the system is doing work on the surroundings, therefore the work is negative. We represent that by these arrows. Okay, so this is it's a very quick, abridged way of this process of thinking, but it's the same thing. All right, let's try another example. Determine the signs for Q and W for the following process. Water is heated to the point of vaporization. So I want you to pause the video now and try to see if you can do this on your own. Draw a system surroundings diagram, draw the arrows, and see if you can figure out the signs of Q and W. When you finish, resume the video, and I'll show you the solution. Okay, so water is heated to the point of vaporization. We can imagine it as something like water boiling on a stove, in which case the heat is coming from the stove and going into the system, which is the water, and it's making the water boil. If the heat is going from the stove to the water, that means heat is entering the system, therefore Q is greater than 0, which makes it positive. Heat going into the system is positive. As the water boils, water particles escape from the liquid phase and go into the surroundings as a gas. They are escaping and pushing against the surrounding air to get to become a gas. In order to do that, the water particles have to work against the pressure of the surrounding air, which means they have to exert a force on the surrounding air so that they can move through it, which means the system is doing work on the surroundings. If the system is doing work on the surroundings, W is less than 0, which makes it negative. Okay, so heat comes from the stove into the water, which makes the water boil. As the water boils, gas particles, or rather water particles, escape from the liquid phase to enter the gas phase, in which case they push against the surrounding air, doing work on the surroundings. If we interpret that as a system surroundings diagram, we can show that heat is entering the system, which makes Q positive, and work is being done on the surroundings by the system, which makes W negative. We'll do one more example that's a little bit different. A hot bar of iron is placed in cool water. The iron bar is the system in this case, and note that metals tend to expand upon heating. So I told you what the system was here because it'd be a little difficult to differentiate whether the water or the iron bar is the system. But in this particular case, we're going to consider the iron bar to be the system. And it's important to mention that metals tend to expand upon heating because we need to know how the volume is going to change throughout this process. So again, I want you to pause the video, try to do this one on your own, determine the signs of Q and W, and then resume the video and we'll talk through it. Alright, so when an iron bar is placed in water, it's going to cool down and heat the surrounding water. So the heat is coming from the iron into the water, which means that heat is leaving our system. Remember, the iron is the system here. Heat is leaving the system, which makes Q less than 0, which makes it negative. Since we know that metals expand upon heating, we can deduce that upon cooling, they will contract, which means the volume is going to decrease. So the surroundings is going to push on the system to compress it, which makes work greater than 0, which makes it positive. All right, so the iron bar is losing heat to the cooler water. Heat always moves from hotter to cooler objects that come into contact with each other. So the heat's going from the hotter iron to the cooler water. Therefore, the surroundings is able to compress the iron and push against it, and the volume of the iron is going to decrease, which means work is being done on the iron, and the iron is our system in this case. So to translate that into our system surroundings diagram, heat is lost by the system, which makes it negative. Work is done on the system, which makes it positive. Alright, so that's the end of this video. In the next video, we'll do a few more maybe complicated examples of heat work sign determinations. And then we'll move on to what this really all kind of boils down to, which is the first law of thermodynamics.